Truth tables. Atomic propositional formulas, that is, the mere proposition symbols, denote states of affairs like it is raining, the train is moving. Such states of affairs, hold or not, are true or false depending on the circumstances. One day it rains, another it does not. It may rain in Helsinki, but not in Warsaw. The train may be moving or not. We call truth and falsity truth values and denote them by the numbers 1 and 0. The more complex propositional formulas, not A and B, A or B, etc., denote likewise states of affairs, only more complicated ones. Intuitively, they are also true or false depending on the circumstances, so they too have a truth value 1 or 0. Propositional formulas of the simplest form, P0, P1, and so on, can have truth value 1 or 0 according to our choice. But if we give them truth values, then the truth values of formulas built from them, such as P0 or P1 and P0 implies P1, will be completely determined by the rules that we give. So giving truth values to P0, P1 and so forth is really the crucial thing. It decides everything else. A choice of truth values for the proposition symbols is called evaluation. If we use propositional logic to investigate everyday phenomena around us, we may take propositional symbols to denote such states of affairs as quote, it is raining, unquote, or quote, the train is moving, unquote. Then a natural valuation would give quote, it is raining, unquote, the truth value 1 if it indeed is raining, and 0 otherwise. And to quote, the train is moving, unquote, the truth value 1 if the train is indeed moving, and 0 otherwise. However, the point of propositional logic is not to investigate phenomena around ourselves as they are, but rather as they could be. It is raining, but it could also be the case that it is not. The train is moving, but it could be also standing. In fact, in propositional logic we study propositional formulas under any valuation whatsoever. This freedom to change the truth values of proposition symbols in every which way is the essence of propositional logic. It is what distinguishes logic from empirical science. In empirical science, one builds on observed facts, which means, in a sense, that the valuation of the atomic propositions is fixed. Mind you, this is not quite true of quantum physics. Also, in scientific tests it may be essential to vary atomic propositions freely. For example, if we drop balls of the same size from the Leaning Tower of Pisa, we may want to vary the weights of the ball and the height from where the drop is made in order to see how the time of descent depends on the weight and the height. Valuations assign truth values 1, that is true, or 0, that is false, to proposition symbols. Thus, a valuation is a function with proposition symbols as its domain and values in the set 0, 1. Valuations are the building blocks of truth tables, which we will next introduce. The truth tables constitute a systematic tool for analyzing complicated propositional formulas. They can be avoided, but they do help a lot. Valuations extend to all formulas by means of truth tables. This extension is heavily based on the analysis of a propositional formula in terms of its main connective and its immediate subformulas. The truth value, denoted V of A, of an arbitrary propositional formula A can be easily computed in terms of the truth values of the immediate subformulas of A and the truth table of the main connective. The truth table of a propositional formula is a table of truth values of the formula and its subformulas under all possible valuations. Before we can build even the first truth table, we have to determine how truth values behave in the logical connectives, such as conjunction, disjunction, negation, implication, and equivalence. The truth tables reflect our intuition of the meaning of each connective. Intuitively, a conjunction A and B is true if and only if both conjuncts A and B are true. This intuition is easily written into the following truth table. In this truth table, we have columns for A and B. These columns indicate all possible truth values for A and B. So they can be 1, 1, 1, 0, 0, 1, or 0, 0. 4 possibilities, because there are 2 truth values and 2 formulas. Then we draw a column for A and B. And in this column, we write 1 for the case that both A and B are true, and 0 elsewhere. So the column is 1, 0, 0, 0. And it indicates our decision that we call the conjunction true, if and only if both conjuncts are true. In truth tables like this, where we have symbols A and B for propositional formulas, it is of course conceivable that A and B are the same propositional formula, and then there would be only 2 rows in the truth table, both true or both false. But we want to draw this truth table in the most general form, and in the most general case, all 4 possibilities are relevant. Intuitively, a disjunction A or B is true if and only if one of the disjuncts A and B is true. What if both are true? We make the decision that we call such disjunctions true as well. Thus, when we now give meaning to the disjunction sign or, we give it the inclusive meaning, that is, both can be true in a true disjunction. As with conjunction, there are 2 columns, one for A and one for B, and a column for the disjunction. We distribute all possible truth values for A and B on the left. We get 4 rows. Then we decide the column of disjunction. The column is 1, 1, 1, 0, which means that we give the truth value 0, false, to the disjunction only in the case when both A and B are false. That means that for the truth value of the disjunction to be true, 1, it is sufficient that at least one of the arguments A and B has truth value 1. So it is good to remember that the truth table of disjunction has exactly 1 row on which the disjunction has truth value 0, namely when both disjuncts have value 0. Negation is a very simple case in this context. A negation, not A, is true if and only if A is false. The negation is a kind of truth value switcher. It switches 1 to 0 and 0 to 1. We now have to decide what the truth value of A implies B is, if we already know the truth values of A and B. Intuitively, A implies B should be true if B, quote, follows, unquote, from A. However, with two truth values, it is not really possible to express the quote follows, unquote concept. We make the decision that A implies B is true if B is true, but also if A is false. So we get this kind of truth table for implication with rows 1, 1, 1, indicating that we want the implication to be true if the hypothesis A and the conclusion B are true. So true implies true is a true implication. The next row 1, 0, 0 indicates our wish and decision to make the implication false in the case that the hypothesis is true but the conclusion is false. So if one makes a false conclusion from a true hypothesis, that implication is considered false. Then comes the row 0, 1, 1. The hypothesis A is false, conclusion B is true. We decide that this kind of implication is true. So, for the truth of the implication, we decide that it is enough that the conclusion is true. Finally, perhaps the most strange row 001. So if the hypothesis and conclusion are both false, we decide that the implication is true. It is good to remember that the truth table of implication has exactly one row on which the implication has truth value 0. Namely, when the hypothesis has value 1, but the conclusion has value 0. This is useful to remember. There are more involved systems of propositional logic which give a meaning to implication which is closer to the intuition of quote follows unquote. The choice we have made works surprisingly well. On the other hand, it renders such unintuitive implications as quote, if the moon is cheese, then 2 plus 2 is 5, unquote, and quote, if 0 is not equal to 0, then 2 plus 2 is 4, unquote, true. Let us look at a real-life example of implication. Let P be the basic proposition, quote, Jukka lives in Helsinki, unquote. Let Q be the basic proposition, quote, Jukka lives in Finland, unquote. Since Helsinki is in Finland, the formula P arrows Q is true, whether Jukka lives in Helsinki or not. This truth is based on Helsinki being in Finland, and it's unaffected if Jukka in fact does not live in Helsinki. The only thing that would shatter the truth of P implies Q is if Jukka lived in Helsinki but not in Finland, in which case we would have to review our geography. Another way to understand the truth table of implication is the following. Think of A and B as subsets of singleton 0. There are just two subsets, empty set and singleton 0 itself. Let us identify these two subsets with 0 and 1. We can now think of A arrow B as quote A is contained in B, unquote. When we now look at the truth table of implication, we can make the following comparisons. Singleton 0 is contained in singleton 0, so first row is 1 as it is. Singleton 0 is not a subset of the empty set, so second row should be 0, as it is. The empty set is contained in singleton 0, so the third row should be 1, as it is. Finally, the empty set is contained in the empty set, so fourth row is 1, as it is.